Welcome to this lecture series in linear algebra. We will continue our discussion on permutations and let us recall what we need or what we did. So we defined what is a permutation. A permutation of a set X is merely a bijection of X with itself. Alright, and we saw several examples. Here is one example of a permutation, and then we discussed the notion of the digraph of it. So in this example, the permutation is this. The set X is the first 8 natural numbers, and this is how sigma behaves. It sends 1 to 3, 2 to 7, and so on. But a graphical way of representing this same information is via the permutation digraph, and this is the permutation digraph of sigma. It is just telling us exactly what it is doing to various elements. Sigma is sending 1 to 3, 3 to 6, 6 to 1 again, and so on. So the permutation digraph is a very useful gadget, and it has a simple definition, so let me not recall it. It should be evident what the definition is. You just use the data and put arrows accordingly. Alright, so let's move on. So we need to talk about cycles. Now the word cycle has already appeared before, because when we discussed a permutation digraph, we saw that there were cycles in it. Here, the word cycle refers to something slightly different. We'll see what I'm trying to say. So let's look at this particular permutation. And we make its permutation digraph. We make its digraph. So we see that 2, 5, and 6 are fixed by sigma. 2 goes to 2, 5 goes to 5, and 6 goes to 6. So they will not be, they will be depicted as lonely in the digraph. We can, if we want to draw loops like this, but it just clutters it. What about the other elements? Well, 1 goes to 3, 3 goes to 7, 7 goes to 4, and 4 comes back to 1. So that is what we depict here. So the digraph of sigma witnesses only one non-trivial cycle. All the other cycles are of length 1. So there is one non-trivial cycle and everything else is of length 1. So such a permutation itself is called a cycle. So there is this graph theoretic notion of cycle, and this graph theoretic notion of a cycle is kind of giving us the notion of a cycle when we talk about a permutation. You are given a permutation, make its digraph. If you witness only one non-trivial cycle, you declare the permutation itself as a cycle, and the length of the cycle is what is also a parameter we want to record with sigma. So formally, suppose we have some positive integer, at least 2, and then we say a permutation sigma of a finite set X. You can think of X as that. The permutation sigma of a finite set X is called a K cycle if we are going to write down. If there is a cycle of length K in the digraph of sigma. Now this may get confusing because the word cycle here refers to the permutation, while the word cycle here is referring to a graph theoretic notion. This is what we are defining, while this is a graph theoretic notion which is already defined. So the word cycle has been overloaded, but I hope no confusion is caused. Okay, so we say it is a K cycle if there is a cycle of length K in the digraph of sigma, and everything outside this cycle is fixed. Outside this cycle is fixed. So in our picture, we have a cycle of length 4, and everything outside this cycle, meaning what? Everything different from these vertices here, meaning 2, 5, and 6 are fixed, which they are. So this sigma is a 4 cycle. Okay, and here is kind of a general picture, if that makes sense. Okay, and we say that a permutation of a finite set X or any set X is called a cycle if it is a K cycle for some K. Okay, so very simple definition. And now let us proceed. So let us talk about disjoint permutations, a very, very simple concept. Let's motivate the definition via an example. The set X is the first 8 natural numbers, And to depict sigma, we have just made the digraph. It's better to make the digraph rather than write down the map. So this is sigma. It sends 1 to 3, 3 to 4, 4 to 1, and 7 to 8, 8 to 7, and fixes these three. And we have tau, whose digraph is here. And here we notice that if sigma moves something, what is sigma moving? Sigma is moving 1, 3, 4, 8, and 7. It is not moving 2, 5, and 6. Whatever sigma moves, tau does not. And whatever tau moves, sigma does not. Okay? So these permutations are disjoint. They are kind of, not interacting with each other, so to say. They are permutations on the same set, but they kind of do not interact. Tau moves 2, 5, and 6, but those are fixed by sigma. Okay, so we can now write down a formal definition. Fix any finite set. And fix two permutations sigma and tau. We say sigma and tau are disjoint. Yes. We'll write a grisly thing. If things which are moved by sigma, right? This set is precisely the set of those x's which are moved by sigma, not fixed by sigma, intersected with the set which is moved by tau, is the empty set. Meaning there is no element which is moved by both. So that's the notion of a disjoint permutation. And since we motivated the definition via this example, the definition should be fairly clear. It's a very, very simple definition. Okay, and now here is a very simple observation again, which we will not prove. It is an exercise. Note that if we have two permutations sigma and tau, which are disjoint, then they commute, so to say. It doesn't matter in which order you compose them. First you apply tau and then you apply sigma is same as first you apply sigma and then you apply tau. Right? So just to verify this, it should be clear. First look at an example, and whenever you want to understand the statement, it's better to look at an example. So here you apply sigma, you get 1 to 3, 3 to 4, 4 to 1. Or maybe let us just verify that sigma tau of anything, let's say 1, is equal to tau sigma of 1. Let's just verify that. So what is sigma of tau of 1? Tau of 1 is 3, so this is equal to sigma of 3. Sorry, what did I say? Sigma of tau of 1. Tau of 1 is 1 because it is fixed. So this is sigma of 1, which is 3. So that is 3. What is tau of sigma of 1? Well, sigma of 1 is 3. This is equal to 3. This is equal to tau of 3, But tau of 3 is 3 because 3 is fixed by tau. Anyway, so just make this computation in this particular example. You will see what is going on and then you can prove it in general. Nothing happening here. Okay. So now for the last thing, it's a theorem, if you will. What we want to say is fix any finite set x and fix a permutation of it, which is not the identity, and it is also not a cycle. So cycles and identity permutations are particularly simple kind of permutations. Suppose we have a complicated permutation. Then sigma can be written as the composition of disjoint cycles. So if it is not particularly simple, you can write it as the composites of particularly simple things. Let's see the proof via an example. Writing a formal proof is not going to help us. So this is our example, which we recalled in the beginning. And this is its permutation digraph. So then what you can do is, suppose I just want to write this particular sigma, this particular permutation as the composition of disjoint cycles. What will I do? Well, consider the following permutations. This is the first permutation where I only retain the red cycle. So in the first permutation, we see that 2, 4, 8, 5, and 7 are fixed, and this is how the others move. So let me box this so that there is no confusion. This is the first permutation. And give me 1 second. What is the second permutation? Well, that is the second permutation. So if you compose the two, you will get sigma, right? Okay. So this is the composite symbol, looks like a 0, but this is the composite of this permutation and that permutation. So here we can write to sigma as the composite of two disjoint cycles, and you can do it for any permutation which is not identity and not a cycle. Even if there were more cycles around, you would have just as many things appearing here as there are non-trivial cycles in the original permutation. Okay, so it's a very simple observation. May look complicated for some reason, but if you just play around a little bit, you will see what's going on. Alright, so as for the proof, I have written one line that this is immediate from the digraph of the permutation. You look at the digraph, you will see what are the cycles that participate in this composition that we want to form. Alright, so that is all that I wanted to say about this. Okay, so as usual, like, comment, share, subscribe, and I will see you next time.